Good morning, everybody. Uh, so today we're going to keep talking more and more about acyl substitution. So let's just recap what we said last time in the form of a problem. Okay, recap. Acyl substitution acid condition. All right, so imagine we have this molecule. React that with excess water, acid, and heat. So draw the structure of the products. There's going to be more than one. So what were we talking about last time? Acyl substitution, acidic conditions. You're looking for an acyl carbon. What's that? That's a carbonyl carbon that is bonded to something that is not carbon and not hydrogen, right? So you're looking for that acyl carbon. And whatever that is not carbon and not hydrogen, that is going to take off from the acyl carbonyl, and the nucleophile is going to take its place. That is the nucleophile minus a proton. Right, so this is what how acyl substitution happens under acidic conditions. So looking at this molecule here, I see there's an acyl carbonyl up here. It's a carbonyl carbon that's bonded to something that's not carbon and not hydrogen. This thing is going to break off. That's going to take off. Here's another acyl carbonyl. It's a carbonyl carbon bonded to something that's not carbon and not hydrogen. This bond is going to break, and that's going to take off. Okay, so let's just do this stepwise, one break at a time. All right, so we would have, let's do this one first. The thing that's not carbon and not hydrogen breaks off. So get, I'm not going to be able to fit all of this in here. It's a pretty big molecule. Okay, so this OCH3 group, that took off. The nucleophile, which is water, took its place. The water molecule minus a proton, right? So I'm not writing H2O up there. I'm writing H2O minus a proton. The other product of this reaction would be HOCH3, right? Where this OCH3 group took off, and it, in a formal sense, it picked up the extra proton that water came in with. Okay, so that would be, is the reaction over? No, because I have another acyl carbon down here. And so the bond between the acyl carbon and the thing that's not carbon or hydrogen, this is going to take off. All right. See, so this, the bond between the acyl carbon and the thing that's not carbon and not hydrogen broke off, and the extra proton that the nucleophile, which is water, came in with, is in a formal sense transferred to the leaving. The other product of the reaction would be that. Right, where here we see the remnant of the water molecule right in there. It's the remnant of the water molecule as we had it up there. Okay, so that's what we were talking about last time. Now, does this look familiar to anyone? Well, we've dealt with him in the past quite a bit, right? This is cocaine. This is what happens when you take cocaine, dissolve it in water, add a little bit of acid to it, and maybe you have to heat it. Okay, so I'm going to try to show you a pretty picture now. Hope this works. Yeah, cocaine. So there's that cocaine molecule. Let me ask you a question. Don't raise your hand. Just answer silently to yourself. Has anyone ever been stopped by law enforcement and subjected to a full cavity search, including stuff done with a flashlight? Well, that happened to me when I was in college, right? I was crossing the US-Mexico border from Tijuana, Mexico to San Diego, California. And they pulled me over in my car and they said, oh, we're going to, we think you're carrying cocaine back into the US. So they subjected me to a full body cavity search. And they brought out the cocaine sniffing dogs. They didn't find anything. They didn't find the stuff because there was no stuff to be found. But being who I am, I became very interested in the chemistry of cocaine and the chemistry of the cocaine sniffing dog. And what it turns out is that cocaine itself has no odor. But when cocaine decomposes, it produces a very sweet smelling compound that can be detected both by human beings and even more so by cocaine sniffing dogs. Okay, so this actually has something to do with what we're talking about. So, get cocaine, wrap it up in a piece of paper, right? Get a piece of paper. Did you know there's acid? The way that paper is made, there's acid all over a piece of paper from the way that cocaine is made. So I get my cocaine. Where's my cocaine? Oh, I didn't bring it. Okay, I get my cocaine and I spread it on this piece of paper and roll up the piece of paper. Roll up this piece of paper like that. Maybe form it into a cigar-looking thing, right? And guess where this is going if you're a drug smuggler, right? I'll leave that up to you to figure that out. So there's cocaine in here. There's acid all over this paper. And where's the water coming from? Atmospheric moisture is enough to provoke this decomposition of cocaine. And one of the products that we get is this guy, in which I see a carbonyl carbon that's bonded to something that's not carbon and not hydrogen. This thing can undergo an acyl substitution. Another product of this decomposition of cocaine is this guy, methyl alcohol, and that's a nucleophile, right? Instead, you know how water is HO, H-O-H. Well, instead of HO, this is HOCH, H-O-C-H-3. That's a nucleophile. That guy gets together with this one, plus CH3OH plus acid, and there's the acyl carbon, the thing that's not carbon and not hydrogen breaks off, the nucleophile minus a proton takes its place. And so what we get, one of the decomposition products of cocaine is this guy. That's an ester. And maybe you know that esters are very fragrant. This is methyl benzoate. This has a very sweet, very flowery aroma. So the cocaine sniffing dog is not sniffing cocaine. Cocaine has no odor. What the cocaine sniffing dog is sniffing is the decomposition product of cocaine, which is this very fragrant methyl ester. Okay, so that's just a recap of what we talked about last time, applied to a practical situation. All right, so now let's talk more about acyl substitution. We talked a lot about acyl substitution under acidic conditions. Let's talk about acyl substitution in base, because we can also have acyl substitution in base. Acyl substitution, basic conditions. So once again, we're going to be looking for an acyl carbonyl. That's a carbonyl carbon that's bonded to something that is not carbon and not hydrogen. I'm just calling that Z to keep everything nice and general. So Z can't be carbon, it can't be hydrogen. Z could be oxygen, nitrogen, halogen, sulfur, a bunch of stuff that's not more carbon, not hydrogen. Under basic conditions, the nucleophile is ordinarily going to be negatively charged, right? This makes total sense. When we were talking about acid-base reactions, an easy way of identifying the base was the thing that had the negative charge, because a base is something that reacts with H+. So under basic conditions, that nucleophile is going to have a negative charge on the nucleophilic atom. Okay, concrete examples. Under acidic conditions, the nucleophile is going to be water, H-O-H. But under basic conditions, the nucleophile is going to be OH minus, right? These are just examples. Under acidic conditions, the nucleophile is going to be CH3OH. But under basic conditions, the nucleophile is going to have a negative charge on the nucleophilic atom. It's going to be something like CH3O minus or ETO minus or something like that. Under acidic conditions, the nucleophile is going to be NH3. But under basic conditions, the nucleophile is going to be NH2 minus. So you get the picture, right? The nucleophile under basic conditions is going to have a negative charge on it. The solvent, and the solvent here is going to play an important role, is going to be the conjugate acid of the nucleophile. So that these two guys, these are the guys that react, but the solvent also present in the reaction mixture will be the conjugate acid of the nucleophile. In other words, HU. Okay, and so now let's talk about the mechanism. It's a lot simpler than the acid catalyzed mechanism. So there is no acid around, it's basic conditions, there is no H+. We're very used to and we're very comfortable with protonating the carbonyl oxygen and then attacking the carbonyl carbon with the nucleophile. That is not what happens under basic conditions, because there is no H+ in basic conditions. Instead, the nucleophile attacks the carbonyl carbon directly. Can't stop there, because if we stop there, we're going to end up with a carbon with 5 bonds. And so we have this tetrahedral intermediate where the nucleophile is in, and all of these steps are in principle reversible. Okay, so the nucleophile attacks the carbonyl carbon, and now what has to happen in every acyl substitution reaction? The thing that's not carbon and not hydrogen breaks on. All right. And so there's our acyl substitution product. The thing that wasn't carbon and wasn't hydrogen broke off. Its place was taken by the nucleophile. This thing Z, that left as a leaving, but it's going to leave with a negative charge on it, because one of the things we believe in is conservation of charge. Okay, so that would be the mechanism of acyl substitution under basic conditions. All right, so it's simpler. This is also reversible. It's simpler, but we'll see in today's lecture that under basic conditions, after the acyl substitution is over, some tricky things might happen. Okay. So that's acyl substitution, basic conditions, mechanism. Let's do some problems. Okay, so that's an acyl substitution. I see a carbonyl carbon that's bonded to something that's not carbon, not hydrogen. The other guy with that negative charge, that's the nucleophile. Basic conditions, it's negatively charged. Draw the structure of the product or the products. The thing that's not carbon and not hydrogen, that's going to break off. Its place is going to be taken by the nucleophile. Its basic conditions, that leaving group, that thing that's not carbon and not hydrogen, emerges with a negative charge. So it broke off. The nucleophile took its place. And the leaving group left with this negative charge. Yes? Okay. Pretty easy. Let's try another one. Draw the structure of the product here. Products here. Okay, this guy's away. Trick question. This is not an acyl substitution reaction, right? There's a carbonyl carbon bonded to something that's not carbon and not hydrogen. This could undergo an acyl substitution, but it's not going to. This is an acid-base reaction. That's a carboxylic acid. This is a strong base. That's an acid, that's a base. It's not acyl substitution at all. It's simply an acid-base reaction where the acid gives up the proton to the base, right? Did I get you, right? Did you think that it's going to be an acyl substitution? Oh no, this reaction has a huge equilibrium constant. pKa of a carboxylic acid is 5. The pKa of an alcohol is 17. The equilibrium constant is 10 to the 17 minus 5 is 10 to the 12. That's a huge equilibrium constant. So just because it fits the recipe for acyl substitution does not necessarily mean it's going to be an acyl substitution. That's not what happened here. Okay, so acyl substitution basic conditions can be tricky, right? Because if the acyl derivative is a carboxylic acid and you feed it a base, you're not going to get acyl substitution. You're just going to get this acid-base reaction. Okay, so let's look at another product prediction problem. Okay, so draw the structure of the product here. I'll give you a clue. Yes, it's an acyl substitution, right? Because OH minus, that's a strong base, but this guy isn't a carboxylic acid. So you're going to get acyl substitution. Draw the structure of the product. But I'll give you another clue. The thing that you think you get is not what really happens. Carbonyl carbon bonded to something that's not carbon, not hydrogen. This is going to break off, and this is going to take off. There's the nucleophile. It takes the nucleophile takes the place of the departing leaving group. So, and notice that leaving group, that thing that's not carbon, not hydrogen, took off with that negative charge on it. And so we're tempted to think that these are the products of the reaction. But if you look at this situation here, and if you look at this situation here, we see that this is a carboxylic acid. It's a pretty good acid. This is a base. These two guys are going to keep reacting. So the acyl substitution is over, but the reaction is not over. So I'm going to put these in brackets, showing that those are not the final products. What has happened here is I've created a carboxylic acid. That's the key word here, a carboxylic acid, in the presence of a strong base. This O minus, that's a strong base. So these guys are going to swap a proton, just like we saw in this trick question down here. And so the final products of this reaction are the carboxylate. It's not the carboxylic acid. The acyl substitution came to a grinding halt, but the reaction didn't come to an end because the acyl substitution created a carboxylic acid and a pretty good base. They traded the proton. They became the carboxylate and the alcohol. So when the product of an acyl substitution or of the reactant of the acyl substitution is a carboxylic acid, you have to be careful whether there's a strong base present that can engage in an acid-base reaction. So acyl substitution base, kind of tricky. Okay, so now I want to get into another feature of acyl substitution, which is reactivity trends in acyl substitution. Reactivity trends. All right, so there are two trends that we have to keep in mind. One of them I'm calling the between group trend, and the other one I'm calling the within group trend. So we have two trends to deal with. The between group trend is easier. Let's attack that first. Okay, so what I'm going to do here is I'm going to write the order of reactivity among the acyl derivatives, because just because something is an acyl derivative does not mean that all acyl derivatives react at the same rate. So that's what we're talking about. Some acyl derivatives are very reactive, and some acyl derivatives are not that reactive. So there's a trend, the between group trend. So what I'm going to put here, I'm going to lay down the law here, and I need for you to memorize this trend. We may have a closed book exam at some point. The most reactive acyl derivatives are the acyl halides. So, you know, the X, that's just our generic symbol for fluorine, chlorine, bromine, iodine, so on. Those are the most reactive acyl derivatives. And then the next most reactive are the anhydrides. So this is a functional group that we haven't talked too much about, but now we need to talk about it. The anhydride, has an oxygen atom that is trapped between two carbonyls. That's how you recognize an anhydride. Okay, now, aldehydes and ketones are not acyl derivatives, because when you're looking for an acyl derivative, you're looking for a carbon that is bonded to something that is not carbon. You're looking for a carbonyl carbon that's bonded to something that's not carbon, not hydrogen. That an aldehyde and a ketone are not acyl derivatives. But to give this more context, I want to show you where aldehydes and ketones are on this reactivity ladder. So an aldehyde is less reactive than an anhydride, and a ketone is less reactive than an aldehyde for steric reasons. So we talked about all of this earlier in the semester. So these aren't acyl derivatives, but this is where they are on this reactivity ladder. Okay, then below the ketones, you have the thioesters. And then below the thioesters, you have the regular esters, and the regular esters are about as reactive as the carboxylic acids. So these two, although they're not exactly the same in the reactivity, they're usually very, very close. Okay, and now we're getting down to the bottom of the heap. The amide is less reactive than the ester. Okay, and so, and then way down here, you have the carboxylates. So I ran out of room. Let me try to adjust my zoom so that you can see that. And so these are the least reactive. So this is the reactivity ladder, the order of reactivity that's exhibited by the acyl derivatives with the aldehydes and ketones that aren't acyl derivatives just thrown in. Okay, so we would like to be able to explain why this reactivity ladder is the way it is, and then talk about consequences of the reactivity ladder. Okay, so the leaving group here, the here would be X minus. The leaving group here, right, because the thing that's not carbon and not hydrogen is going to break off, it's going to take off, would be a carboxylate. Aldehydes and ketones aren't acyl derivatives, so there's no leaving group there. The leaving group with the thioester would be this thiolate. The leaving group with a regular ester would be an alkoxide. The leaving group with carboxylic acid would be hydroxide. The leaving group down here would be Nr2 minus. And the leaving group down here with the carboxylate would be O2 minus. Okay, those are the leaving groups. And I put a negative charge on everything. Whoa. And now let's look at the conjugate acid of the leaving, right? So now just slap a proton on all of these negative charges. HX, so this could be something like HCl or HBr. The leaving group, the conjugate acid of the leaving group here would be a carboxylic acid. The leaving group here would be a thiol. Here it would be an alcohol or water. Here it would be an amine. And the conjugate acid here would be OH minus. Okay, and so now let's whip out that pKa table and identify the pKa's of all of these conjugate acids. So the pKa of HF, HBr, HCl, and HI, they're all different, but they go from -10 to +3. Okay, the pKa of a carboxylic acid from that table is 5. This is 10. This is something between 16 and 17. This is 35. What's the pKa of OH minus greater than 50? That's not on the table, but I'm just telling you that. Okay, and so what we see here is the explanation for this between reactivity trend. It turns out that the best leaving groups, the most reactive leaving groups, are the weakest bases. Best are the weakest bases. And we know when we were studying acids and bases that a strong acid has a weak conjugate base and a weak acid has a strong conjugate base. The best leaving groups have the strongest conjugate acids. But really the important thing to remember is that the best leaving groups are the weakest bases. And we see a very nice monotonic, no hiccup trend in leaving group ability. So that's the best leaving group. That's the weakest base. That's the strongest conjugate acid. Now this number got a little bit bigger. This is a stronger acid than these guys. That's a weaker. This is a weaker base than this one. So this trend is very nice, and it explains why this group is more reactive. This acyl derivative is more reactive than this other one, because the best leaving groups are the weakest bases, and they correlate very well to the pKa's of the conjugate acids. Always remembering that a strong acid has a weak conjugate base. A weak acid has a strong conjugate base, and strong bases are terrible leavings. All right, so that explains our between reactivity, our between group trends, so that we can just say Every acyl halide is more reactive than every amide. Every bioester is more reactive than every ester, and so on. Okay. So now what I want to address is a very nice question that someone asked me at the last lecture. What happens when you have a carbonyl carbon that is acyl on one end and acyl on the other end, on both ends? Now we can explain and understand what's going to happen. So something like this. React that with water, add acid, probably have to heat it, draw the structure of the product. Oh, and by the way, I only have 1 mole of water here. Right? I don't have enough water to take care of both sides of this acyl derivative, just enough on one side. Draw the structure of the product. Starting material here is acyl on both sides. If you cover up this part, you see a carbonyl carbon bonded to something that's not carbon, not hydrogen. That's acyl. If you cover up this side, you see a carbonyl carbon that's bonded to something that's not carbon, not hydrogen. That's acyl. What's going to happen? Well, if you look at that reactivity ladder, we see what's more reactive, an ester or an amide. An ester is more reactive than an amide. So what's going to break off? The ester. The amide's not going to do anything. So that reactivity ladder is a way of predicting what will happen when you have a compound that is acyl on one end and on the other. So this is actually a pretty important kind of compound, not so much for biochemistry, but this is called a urethane. Maybe you've heard of polyurethane, which is used as a varnish and so on, plasticizer. So this is a urethane. It's an important industrial chemical. So water and acid, what happens? The ester breaks off. Yes? Okay, so what about something that looks like this? CH3OH, acid, probably don't even have to heat this. Draw the structure of the product. That's an acyl carbonyl, that's an acyl carbonyl, that's an acyl carbonyl. But this is an anhydride. They're more reactive than a thioester. So the thioester is not going to react. It's going to be the anhydride that reacts. So we get let's say we have excess. So that's going to break off. That's going to take off. The nucleophile will take its place. So we could get something like that. Or this is also an anhydride. This could break off, and this could take off as well. So I'm going to call this set A. I'm going to call this set B. So this would be the product when the A bond breaks, the products when the B bond breaks. So that broke, that took off. So we would get that. So this would be the set that we would get if the B bond breaks. It's hard to predict whether that bond would break or that bond would break. The point of the problem is I have an anhydride versus a thioester in the same molecule. The thioester is less reactive than the anhydride. Okay, so that's the between group trend. Pretty simple. We just have this order of reactivity, and if you memorize that, it makes solving these problems a lot quicker. Now, the within group trend, that's a lot trickier. The between group, the among group trend. Okay, what if we're looking at a bunch of esters and they're all esters, or we're looking at a bunch of amides and they're all amides? The between group trend can help you there, right? The between group trend is good for sorting out whether the ester is more reactive than the amide, which it is, or whether the acyl chloride is more reactive than the acid, which it is, and so on and so forth, right? That's what the between group trend is for. The among group trend, this is what we use when we're comparing a bunch of esters against each other, or a bunch of amides, so on and so forth. So this is a lot more complicated. And so we have to, in order to sort this out, we have to remind ourselves about our carbonyl reactivity trends in general. And that is big, bulky groups at the carbonyl retard reactivity. So if you're looking at a bunch of acyl derivatives and they're all esters, the one that has the big bulky group at the carbonyl is going to be less reactive than the one that doesn't. So a concrete example of this would be, that's an ester. And this is an ester. Right? Which one is more reactive? It's going to be this one, right? Because this big chicken foot at the carbonyl is slowing down the reactivity. This is what I mean by the among group trend, or one of them anyway, where we're looking at two esters, but these two esters are not equally reactive. This ester over here, which has the smaller group at the carbonyl, would be more reactive. That's just a principle, a general principle of carbonyl reactivity. Wow, almost time to give up. Okay, next is that remember that the best leaving groups are the weakest bases. And remember that the weakest bases have the strongest conjugate acids, right? And when we're looking at, and another principle that we encountered earlier in the semester is that electron withdrawing groups increase acidity. So this is another thing that we have to consider when we're looking at two esters or two amides and we're trying to decide who is more reactive than whom. So a concrete example here would be, all right, so that's an ester. And this is an ester. And notice that at the carbonyl, the bulk of these two groups is about the same. So we're not looking at this trend up here about the big bulky groups. Now what we're looking at is just the quality of the leaving. So tell me, which one of these esters is more reactive? Are you guessing? Are you trying to guess which one of these esters would be more reactive? Well, this is a nitro group, and nitro is an electron withdrawing group. Electron withdrawing groups increase acidity if this guy, he increases acidity. If he increases acidity, what does he do to basicity? Decreases basicity, right? Because a strong acid has a weak conjugate base. So this guy is increasing acidity. He's decreasing basicity. So this leaving group is a weaker base than this one. This guy is going to be the more reactive ester, right? So this is another example of what we mean by this among group trend. So you're looking at the steric bulk at the carbonyl, at the acyl carbon, and we also have to make conclusions about the leaving, its basicity, being the most important thing. Okay, it's time for me to head off to my next Zoom. But I'm wondering, before we finish up, any questions about anything? Okay, so next week we'll continue talking about the among group trend and do a bunch of problems that hopefully will illustrate that. So any questions about anything? All right, well, have a good day.